Hi, my name is Attila Gyulashi. I'm a research scientist at the Ski Institute at the University of Utah, and I'd like to thank Julian for inviting me to give the Introduction to Topology-Based Analysis talk. I myself am not a contributor to TTK, however, I have been involved in topology-based analysis for almost 2 decades, and I'm excited for what TTK is doing in terms of bringing topology-based analysis methods to the larger scientific community. So, why do we do topology-based analysis? Well, you can think of abstraction as a continuum from data, which is actually just voltages on chips, all the way to language, which is the where we actually do our critical thinking and problem solving. Where you could think of the first layer of abstraction being, representing voltages as ones and zeros, then grouping those into floating point values that are distributed spatially. Going from the other end, you can tell a domain scientist the word tetrahedrane, and the chemist will know that's a C4H4 molecule, which is a tetrahedral arrangement of carbon atoms with hydrogen sticking off of them. And there's certain levels in this abstraction stack which are better for programming or better for problem solving. And this is what topological analysis does in terms of data analysis. It provides a language for reasoning about the kinds of features that are in our data to make concrete analysis. So let's give an example of this. On the left side, we see a satellite image of the University of Utah, and on the right side is a map representation of the same thing. For the task of finding directions, the map view is much more useful because you can write a combinatorial algorithm to solve the shortest path problem, and it gives you a result that is easily interpretable and repeatable. However, in general, scalar functions don't come with their own, or scientific data doesn't come with its own streets and intersections representation. This is where topology comes in. These are intrinsic properties of functions that can be encoded in something like a street map. Here, for instance, I show two encodings. One is based on gradient features, that's the Morse-Mel complex, and then the other is the contour tree, which is based on contour-based features. So, past applications of topology-based analysis have included everything from molecular analysis to materials analysis, battery design, neural pathways, looking at additive manufacturing technique evaluation, geologic interpretation. This barely scratches the surface of the things that topology can be applied to. So what the heck is topological analysis anyway? We've all heard the cliche that to a topologist, the coffee mug is the same as the donut. And this is because there's one single connected component with one non-contractible cycle or loop. Just the same way, on the top left here, the two blobs doesn't have the same topology as the one blob, and this is based on a notion of connectedness, where if you pick any 2 points inside the single blob, you can find a path also inside the blob to connect them. Whereas for the two blobs, you could pick a pair of points where there doesn't exist a pathway that connects them inside the blob. So connectedness is one topological attribute. By the same logic, the star is the same as the blob because any 2 points you pick in there can be connected by a pathway inside the star. And same thing for the blob. The coffee mug is not equal to the blob because I can pick a cycle or a closed loop in the coffee cup donut that is not contractible. That is, you can't squeeze it down to a point. Whereas any closed loop inside of my blob, you can contract down to a point. So topology then tells you about the connected components, the cycles of various dimensions, etc. Again, you might ask, well, what the heck does this have to do with my scalar valued or vector valued data? Well, for scalar valued data, what we could look at is the anatomy of a scalar function. So the topology of a scalar function relates to the topological changes during a filtration. Here I have a typical 1D scalar function defined over some domain, and the function values are the range. Now, what a filtration does is I'm going to include successively more pieces of my subdomain that are less than or equal to a filtration value. So as I sweep this value from minus infinity to positive infinity, what happens is more and more pieces of my subdomain are included in the subdomain. And if I pause this animation right after we go through a minimum value, you'll notice here on the x-axis, a connected component of the subdomain appears. As we go past other critical minimal values, other pieces appear. So now the topology of my subdomain has changed in that the number of connected components has increased. As I pass a maximum value here, two of my connected components that I had earlier merge together. And so again, the topology of the subdomain changes. Again, another maximum merges more connected components, etc., until you've your subdomain equals the entire domain. Okay, so now we see how the topology of the subdomain actually changes during this filtration. We can also look at the persistence of a topological feature, which is how long it persists in our filtration during the sweep. So for instance, this minimum appeared at a minimal value as its own connected component, and it was merged into another connected component, so the unique topological or unique connected component disappeared at a maximum. So this unique connected component only existed for a short time in the filtration. And the difference in function value is called the persistence. And this, we can apply this thinking to everywhere where the topology of our subdomain changes. And what this does is create a pairing of critical points between the birth of a feature and the death of a feature. And one nice thing about topology is now that we've encoded the abstract representation of when features are born and die, we can start thinking in terms of topological scales as well. For instance, I can think about what does this function look like if I were to remove the small pieces or small topological features. We could simply remove those from the abstraction and see what the function looks like at these various topological scales. So here I've removed two of my small features, and what we have is a function with 2 maxima and 3 minima rather than 3 maxima and 5 minima. Or sorry, 4 and 3. Okay, so now we know that topology is roughly related to the, or in applying topology to scalar values, we're really talking about the topology of this filtration. What the heck is it good for? Well, the basic notion is that the features of interest in my scientific study are going to be related to my topological features. For example, we already saw that critical points encode the birth and death of topological components, and for the critical points occur where the gradient is 0, so little flat pieces of the function. And in one dimensions, we have maxima and minima. So working with just the critical points, we may want to learn how features are distributed by their function value inside of this function. And one thing that lets us do that is a persistence diagram. So a persistence diagram takes a single pair of critical points, a minimum and maximum in this case, and puts it on a plot where on the x-axis you have the function value of the birth of that feature, and on the y-axis the death of that, the function value of the death of that topological feature. And what you notice here is that small features like the orange and the purple are mapped closer to the diagonal than large features like the red, green, and blue. So just looking at the persistence diagram tells you where in the function value range the large and small features are distributed. And this can provide a useful signature for your function. Another way to look at this similar data is put persistence on the x-axis and the count of the number of minima or number of maxima on the y-axis. And this is called a persistence plot. And this is another kind of signature which also can tell you where there are stable thresholds. Maybe the phenomena under study actually has, natural topological scales at which features appear. And these could appear as flat regions in the persistence plot, where the intuition is if you move your persistence simplification threshold a little bit to the higher or lower, for instance, the count of features doesn't change. So maybe this motivates you saying that this is actually a stable analysis result in topological scales. Another way we could use the topology to analyze a function is to look at the actual components that are created and when they merge. So here I'm simply coloring the domain based on a unique identifier for the connected component during this filtration. This is called a join tree, and the abstraction is shown right here in this tree. Now, what this lets us do is do some interesting analysis. For instance, we can look at just the leaves of this tree. This gives us a notion of the spatial extents of local features. So we could define something called a local valley based on the connected component created by each of the minima. We can even do this in the context of persistence. For example, by removing this small persistence pair here, corresponding to removing this, what we've actually done is just look at a subtree of the connected component. And this lets us answer questions, for example, what is the local value at a particular topological scale at persistence x? Of course, we can play the same sweep from positive infinity to minus infinity. This gives us the split tree, which gives us a means of defining something like a local peak. Related concept is decomposing the domain into locally monotonic regions. So here what I'm showing is basically each of these segments, the plot between the critical points is monotone, uniformly increasing. And this divides our domain into nodes, which is the critical points, and arcs, which are monotone pieces between them. So this is a cell complex. Now what we can do is take critical points. For example, if I take a maximum and the monotone cells around it, I can define something like mountains, which provides the decomposition that we see here. Or I could take the monotone pieces around minima and create a decomposition into basins. And this is often known as the watershed transform. And just as with the join and split trees, we can also do this for basins and mountains at some specified persistence, and there are rules governing how these regions merge. Okay, so what does all of this look like in 2D and 3D? Because 1D functions are only so interesting. Well, for a two-dimensional function, we can play the same exact game, which is we can start a sweep. Sorry, just skip the slide here. So we'll sweep from minus infinity to positive infinity, and our pink region here is the subdomain with function value lower than our sweep value. And again, what we'll notice is that, you know, at minima, features or connected components appear, and then at saddles, they merge together. Another possible topological change now is there are saddles that do not merge two distinct connected components, but instead complete a loop. So here are the loops I've circled at this one particular filtration threshold. So again, here's the notion that critical points occur where the topology of the subdomain changes. And now, as the function value goes past a maximum, you have holes that get filled in. The monotonicity in 2D is a generalization of the one-dimensional monotonicity, where I take my contours and now I break them up into monotone chunks based on integral lines. So an integral line is simply a curve that is tangent to the gradient at every point, and here I've drawn them in also. You'll notice they're orthogonal to the contours. And if I take the pieces of the contour that flow according to these integral lines from the same origin to the same destination, so the upper and lower limits of this integral, then I can start dividing my domain based on this equivalence relation. So here's a coloring of all the pixels based on unique regions in terms of origin and destination in the gradient flow. What this actually is a segmentation of the domain into a cell complex where we have quadrilateral patches that are bounded by arcs, which are then bounded by nodes. This is another way to encode the topology of the scalar function. Okay, so now I have my two-dimensional scalar function. We could do the same exact kind of games we played in 1D in terms of the kinds of things we can study about the topology. We can look at persistence curves, which now have maxima count and minima count. We could look at persistence diagrams, which now show the minima one saddle persistence pairs as well as saddle maximum persistence pairs. And we can do our same join trees, split trees, and the contour tree, which is the tracks the evolution of individual contours, not pieces of the subdomain. So here I've drawn the trees embedded inside the domain, and one can start imagining how if we wanted to extract different kinds of features from our scalar function, we could query this tree structure and the associated segmentation of the domain in certain ways. And our monotonicity also gives another way of segmenting the domain, which I'll go into in a little bit. So what can we identify as phenomena features in terms of the join tree and split tree? So here are the base segmentations they give. One thing we can do is look at our local valleys again and what they look like in 2D. In this case, we identify the regions associated with leaves of our tree or entire subtrees. This gives us a local threshold for identifying something rather than global thresholds. So this could be more adaptive to the particular intensities in the function. Here's the definition of the local peaks illustrated. And you'll notice there is no global threshold which would give me this segmentation. It is purely adapted to the local nature of the data. For the Morse-Smale complex, now again we can group the monotone regions around a maximum to give us mountains. The boundaries of those regions gives us valley lines. We could group the monotone regions around a minimum to give us basins or the watershed transform, and the boundaries of that gives us ridge-like structures. Oops. Now, I'm not going to go through the animation in 3D because it becomes really complicated to see like everything is self-occluded when we do the filtration, but we could take a three-dimensional function like this, 8 Gaussians arranged in a cube, and play the same games. Where here the join and split tree allows us a certain kind of segmentation, just as in 1D and 2D. Now in 3D we have 4 kinds of critical points. We have minima, maxima, and 2 kinds of saddles. So the persistence diagram will reflect that kind of pairing. We can also do persistence curves in 3D. The Morse-Smale complex, in addition to having our usual mountains, valleys, ridge lines, and valley lines, also has saddle connectors, so saddle-saddle lines, ridge surfaces, and valley surfaces. So these ridge surfaces separate mountains, and the valley surfaces separate the basins. Okay, so we've defined a bunch of topological abstractions that are intrinsic to scalar functions. How do we actually use this in analysis? Well, the first step is to start translating back from things a scientist might be interested in into our topological language. So a scientist may say, I need to extract, identify, count, or measure extreme points. So we could look at a persistence diagram or a persistence plot to start that analysis. They may be interested in local peaks or local valleys as phenomena of interest, and then we know we need to compute the leaves and branches of the joined, split, or contour trees. They may be interested in ridge-like or valley-like structures, which could be the saddle extremum arcs of the Morse-Mill complex. They may be interested in basins or mountains, which now we know are the ascending, descending segmentation IDs of the Morse-Mill complex, or separating surfaces, which again we can extract from the Morse-Mill complex. And even this is a fantasy because no scientist is ever going to come to you and say, I need to extract or identify mountains. Instead, they're going to come to you with a much more generic term of what they're interested in. Here's some examples that I've encountered. So what we're going to do is take a scientist's description of the phenomena they want to analyze and create a hypothesis in terms of the topological language for creating a robust feature definition. So for example, a scientist says, I want to quantify the porosity of this metal foam on the left. This is not a topological description or any kind of robust description of what they're actually looking for. So through iteration with the scientist, we can come up with a reasonable hypothesis that what they actually want to do is measure the total length and number of cycles in the ridge-like filaments of the Morse-Mill complex of this data. Or a scientist may say, I want to measure the bubble formation rate. Well, we can translate this into our topological thinking in terms of, for example, we have a hypothesis that you can measure this by looking at the evolution of stable descending two manifolds, or the mountains, on an isosurface of mixed refraction, the height function on an isosurface of mixed refraction. Or a scientist may say, I want to identify ignition kernels. So you could think of that as, well, this is local peaks of the split tree in regions of the temperature field below the flame base. Or the scientist says, I want to measure the deformation of cavity walls in my foam. Well, what we could do is say, well, we know how to separate or compute these separating surfaces between basins. We could measure the deviation from a plane for those surfaces. So these are all hypotheses for how the features appear but what it lets us do is formalize the definition in terms of the topological language. Now, I would argue that these definitions are never set in stone, and deriving the topological equivalent for a phenomena of interest is always a continuous cycle of evaluation, where the domain expert poses a problem, we can propose an abstraction and language that solves that problem. Then you have to go back and use something like TTK to actually extract those features. Then a very important step is visualization and analysis, and I would argue iterating with the domain scientist and saying, well, here's the features as you describe them to me in our proposed abstraction. This is what we computed. Does this solve the problem? And this is a continuous cycle that requires many, many layers of iteration. So let's look at some use cases. So first we'll look at a relatively straightforward application of a topological abstraction, namely to extract vortex structures. So a well-known approach for extracting vortices is to use an indicator function like the Q criterion, but also a well-known problem is that there are massive differences in the local speeds and scales of vorticity, meaning that there's no good threshold of Q that will extract vortices at these different scales. So directly applying our topological knowledge, we can theorize that what we're actually looking for is local peaks of this Q criterion. So that will apply our split tree and look at the leaves and subtrees of the split tree to create a non-uniform segmentation of this domain. So in particular, we define a function relevance, which basically looks at the local height of a subtree in our split tree and rescales the function based on this local height. So what this lets us do is now create a function for which a constant threshold of relevance will extract vortex tubes at different scales. Okay, that was simple. In this next example, the mapping to topological method was much more complicated. Basically, this domain scientist had this experiment where a micrometeoroid impacts a metal foam, and they want to know what is the loss of porosity. So our very first step was to convert this data into something that topological representations are good for. So the data came in as a binary field of 1, which is metal, or 0, which is vacuum. And our hypothesis was by looking at a distance function from the interface surface, the ridge lines in the Morse-Mill complex would trace out the filamentary structure of this material, and we could look at the length and number of cycles in this filament structure. So to test this hypothesis, we generated our own test data set, which is just putting material randomly along a sine curve and a squiggle curve, a corkscrew curve, and see if we apply our distance function, compute the Morse-Mill complex, and look at the ridge lines of this function, can we actually extract what we think we should be able to? So we did this, and here's a plot of the two saddle maximum pairs. These are the critical points that bound the ridge-like arcs. And our intuition is that the high-valued saddle and maximum pairs should correspond to the center line of this structure. So now, testing our hypothesis on this artificial example, we could see that indeed we traced out the expected structure. So this gave us the confidence to then apply it to the real-world data. So for each time step, then we computed the distance function, the Morse-Mill complex, performed persistent simplification, and extracted the filamentary structure, identifying the total length of the filamentary structure and number of cycles to quantify the porosity. And we built a tool for the domain scientists to be able to explore basically the parameters and thresholds involved and verify visually that what they were extracting was actually what they thought they were extracting, and what they were measuring was the correct thing. And this tool, for example, was useful to identify that they had to remove kind of the base of the material from consideration in the length measurement. Another thing that the topology let us do is define an interface surface between the outside of the material and the voids on the inside as the ascending two manifolds from one saddles. And this, in fact, reconstructs the kind of the surface of the material, so you could directly measure the impact crater on this porous material. So in this example, the domain experts were interested in understanding how the walls of this foam deformed. Now, our hypothesis was you could simply extract the basins from the Morse-Mill complex and look at the separating surfaces between the basins. One of the challenges basically became that, what is actually in the data was not clean. For example, this is a CT image of a metal foam, and there's a ton of artifacts. So it turned out that after computing the Morse-Mill complex and providing visual feedback, there was no topological scale even at which the basins would reliably extract the grains inside of this foam. And when we asked them, well, how do you actually extract these things by quote-unquote hand, even though they weren't doing it, they said, well, if you kind of squint, you kind of see the path of the boundaries of these grains. And so what we can do is say, cause the computer to squint by applying a median filter and then Gaussian blurring it with a small filter radius. And what that does is now our topological segmentation aligns much better with the expected segmentation the users had, and we can look at things like the boundaries between these grains. Okay, so now some words of wisdom that I've accumulated over the past 2 decades, which is, first, I've never gotten the abstraction right on the first try. It's always iteration with the domain scientists, And part of that is visualize, and visualize early and often, which is you think you're computing a persistence diagram and it's telling you one thing. Actually look at where those critical points are coming from. Because topology finally tells you what is in your function, not necessarily what you think there should be. So there have been many cases where intellectually we come up with a feature definition, and when we apply it to actual data, we come to a crashing halt because what is in the data is not what we think of there should be. For instance, we've seen this with CT scans and beam hardening, or other kinds of artifacts. And with that, I'm out of time, and I'll take some questions. Thank you very much.